Alright, so this is the explanation for the cart speeding up to the right or in a positive direction. For this, we expected our position time graph to be parabolic in nature and upward opening, parabolic to be exact. And we achieved this ever so slightly, but still achieved it, as we can see here in our position time graph. For this, I just took the linear fit and I got a slope of 4.892 inches per second, which is our average velocity for our cart. I also got a y-intercept of negative 2.127 inches, meaning that at time equals 0, the cart was negative 2.17 inches behind the origin. From this, we got a equation to find our position on any time between these two intervals, which is just our slope times our time plus our initial position. Our slope, which is 4.829 inches per second, or our average velocity times our time at any time, plus our initial position, which is negative 2.17 inches. And we expected this for a cart speeding up in a positive direction because he has an acceleration, meaning that the velocity graph should be linear, and for a velocity graph to be linear, we have to have a parabolic um, graph for a position time graph. For our velocity time graph here, we got I took the linear fit for this, although we did want a linear line. The world isn't perfect, and we got this, which is very close, I think, to a linear line. For the from this linear fit, we got an equation of v equals mt plus b, which is a velocity at any time between these in this interval is equal to our slope times our time plus our v naught, and our slope or our acceleration for this cart is 1.168 inches per second squared. So this is saying that for um, that our cart is increasing 1.168 inches for every second, inches per second for every second. We also got a b or a y-intercept, or otherwise known as a v naught, since this is a velocity at times equals 0 of 2.093 inches per second. So at time equals 0, we had our cart was going at a velocity of 2.093 inches per second, and this is a pretty good line for what we wanted in the terms of the real world. For our integral, or our area under the curve, we got 23.18 inches. This is actually our change in position because the area under a velocity curve is our change in, or our displacement or change in position. And since our position started at 0, or at least we wanted it to be starting at 0, we can check this by just subtracting the last one, the last position from the first position, which does seem about right considering our initial position is supposed to be negative 2.127, and our position here says it's at about 25. So yeah, it works out. And that's that.